Alright, let's look at friction in Chapter 5, Section 5.2. So first, a couple definitions. Static friction. Static friction is the force exerted on one surface by another when there is no motion. Alright, so when something's stopped. Think about when you need to push a car, you're pushing against static friction initially. Once you get it rolling, we have kinetic friction. And kinetic friction is the force exerted on one surface by another when one or both surfaces are moving. So this is the friction that you have when your tires are rolling. So let's look at the friction equation, and this is something you can put on your blue sheet yourself. Friction is proportional to the normal force. Now remember, the normal force is the force perpendicular to the surface. So at this point in our careers, we've always been looking at weight, because that weight acts straight down, and the normal would be perpendicular to it. But it could also be on inclined plane, and let's say we had a box here. The normal force would be perpendicular to the surface. Okay? And we'll be looking at that in more detail soon. Our equation is the frictional force is equal to this new letter, which is the coefficient of friction, times the normal force. So, definition of terms. We'll be doing that in just a minute, so we'll just look at this as the basic equation. Factors that affect friction, it depends on the materials in contact. So you can have wood on wood, socks on wood, socks on carpet. Think about sliding across the gym floor versus sliding in your living room, which has carpet, and rubber on ice. So those are all coefficients of friction that we can look up. Factors that don't affect friction, it's the material, not the surface of the material, that affects the friction. So ice, glass, and rubber can all be made smooth. Ice has a low coefficient of friction, glass has a medium, and rubber has a high coefficient. Speed doesn't affect friction. All it depends on are the two materials and the normal force. So, static friction. Let's look at what all these variables mean. So, this first one is defined as, that's 3 lines, the frictional force, let's write it a little differently, the static frictional force. This guy is called the coefficient of friction. And Fn is defined as your normal force. Now, when you have kinetic friction, everything looks the same, except your coefficient of friction will have a different value, because now this will be your coefficient of kinetic friction, and it's a different value than static friction. Kinetic is moving friction, and static is when something's stationary. So coefficient of friction, here's just a few values that I took from a table in the Glencoe book. When it's static, think about trying to push a car on dry concrete. You have a static friction of 0.8. Once it's rolling, it's 0.65. Once the concrete's wet, look at how much it changes. And there's a couple of others which we'll use. So, let's look at our first example problem. You're pushing a 25 kilogram wooden box across a wooden floor at a constant speed of 1 meter per second. How much force do you exert on the box? So, first a free body diagram. Draw your box. In the downwards direction, we have its weight. In the upwards direction, we have the normal force. We have some sort of push from you, and we have, in the opposite direction, I'm going to make this longer so we can read it, but a lot of times this will be really short, and this is our frictional force. It's moving, so it is kinetic frictional force. Now, it's a constant speed. What's the acceleration? I'm sure you said 0. So what we're looking at is the summation of all the forces that allow this box to accelerate. Now, the acceleration is 0, so we're looking at the summation of all the forces will give us a value of 0. Now, our forces, the box isn't going up and down, so we're looking at the horizontal forces. To my right will be the positive, so my push minus the frictional force is going to give us m times a, which is 0. So remember, this summation is just all the forces acting on the box. I'm trying to figure out that force that I'm pushing with, so I know the push is equal to the kinetic frictional force. So we have some more work to do before we can solve the problem. I'm going to go to the next page. Eventually. There we go. Now, we just said that F push is equal to the frictional force, kinetic frictional force. Well, that kinetic frictional force is equal to the coefficient of kinetic friction of wood on wood times the normal force. Remember, your normal force is weight, m times g. So we're trying to solve for the frictional force. If you go to your table, UK for wood on wood is equal to 0.2. There are no units on it, it's a ratio. Your mass was 25 kilograms, and gravity is 9.8. So, my kinetic friction is 0.2 times 25 kilograms times 9.8 meters per second squared. My push has to be equal to the frictional force, which is 49 newtons. I'm going to say equals F push. Kind of cool, but complex. A lot of thinking has to go on. Let's look at another one. Blank page here. And example 2. If the force you exert on the box is doubled, what is the resulting acceleration? So, we just got an answer on our last problem that the force of the push was 49 newtons, right? So, I'm going to say my new push is 98 newtons. So, here's our box again. You got the push going this way, has a new value. You still have the frictional force. We now know what that is. We still have gravity, and we still have the normal force. We're trying to find the summation of the forces, which will give this box some acceleration. We're trying to find A. So, going back to what we know F push minus your frictional force is going to equal your mass times acceleration. Putting in our numbers, we have the push is 98 newtons. From the last problem, we knew the frictional force was 49 newtons. I'm going to divide by the mass, which is 25 kilograms, which gives us our acceleration. And A will be 1.96 meters per second squared. So on this one, we plugged in a new number for the push and calculated a new acceleration. Our third example. Suppose a 10-newton wagon with rubber tires is resting on concrete. The coefficient of kinetic friction is 1.02, pretty high. If a person weighing 200 newtons sits in the wagon, what is the force needed to pull the wagon at a constant speed? So things we know. We know that UK is 1.02. We know the total weight of the wagon with a person in it is 200 newtons plus the 10 newtons, which is equal to 210 newtons. That is equal to the same magnitude as the normal force. Our acceleration, if we're at a constant speed, that's going to be 0. Our goal is what force is needed to pull this wagon. So let's go to the next page and make a free body diagram. So we have this wagon. It has its weight in the downwards direction, normal force in the upwards direction, friction's working against it, and some sort of push in the opposite direction. Our goal is to figure out that force. I'm just calling it a push. I guess I could call it a pull. Let's change it. F pull. Because it does say in the question, what force is needed to pull the wagon at a constant speed? So, we're looking for the summation of the forces will give us mass times acceleration. We know that A equals 0, and our forces, we have the pull with friction acting against it equals the mass times 0 is 0. So now I have F pull, again, is equal to our frictional force. So now we're going to calculate that frictional force. The frictional force is equal to UK times the normal force. So our frictional force is 1.02, that was given in the problem, times the normal force, which is 210 newtons. Calculate that, and you have 214.2 newtons. So remember, your pull is equal to the frictional force since we're at a constant speed, so F pull is equal to 214.2 newtons. You need just enough pull to overcome friction. All right. Let's do another one. A shuffleboard disc is accelerated to a speed of 5.2 meters per second and released. If the coefficient of kinetic friction between the disc and the concrete cord is 0.35, how far does the disc go before it comes to a stop? The cords are 16 meters long. Well, we want to know how far, so we need to know how big a push is perceived. Maybe. So, maybe not. Let's see what we know. We know VI is 5.2 meters per second. It's coming to a stop on the shuffleboard court. All right, there's the stop. Now the distance, even though it gives us that 16 meters, it's asking us how far it goes. So that's a little confusing, but D is our unknown, and we need to find A, and that's where we're going to use our summation of forces idea. So thinking about this disk, let's draw a free body diagram. There's the disk. It has its weight, so it has a normal force. Now, the only thing slowing it down once it's released is the frictional force. So, my summation of the forces on my disk is just the frictional force equals mass times acceleration. Now, we're going to take our F, our frictional force, and break it down into what it really means this time. So, we know that it's the coefficient of friction times the normal force equals mass times acceleration. Now, we don't have a mass of the disk, but watch what happened. Your coefficient of friction times mg, because normal force is equal to mg, equals mass times acceleration. Look what happens to your mass. It goes away. We know what UK is, we know what G is, we can find A. UK was 0.35 G. Remember, G is 9.8, so I'm going to say 0.35 times 9.8 meters per second squared. And that is going to give us our A. I'm sorry, I ran out of room, but when you calculate that out, you get 3.43 meters per second. So you don't need to know the mass. Now we know the acceleration. It is negative because it's slowing down. That is something you would have to put in there yourself per second squared. I don't think I put the squared on it. Now we can find D. It's a regular kinematics equation. So let's go to the next page. We have, do that. I want to find A. I'm going to use, I want to find D. D is equal to Vf squared minus Vi squared divided by 2A. 0 is subtract 5.2 meters per second squared divided by 2 times negative 3.43 meters per second squared. Work your magic with your calculator, and I have an answer of 3.94. That's how far the shuffleboard disc will go before it slides to a stop. Interesting, huh? I have one more for you. And I think I'm going to stop here because I bet I'm out of time. End of show.